so many people here tonight. And I'm delighted that Fabian has come. I met him 2 years ago, I think, in Delft, where we had a very public discussion about whether it was possible to make a mathematical representation of aesthetics. And Fabian is a computer scientist, and he said no, but I'm still trying to convince him that you can write code for aesthetic decisions in architecture. Fabian has a very interesting background. He's a computer scientist. The practice design to production is what I think of as one pole of the new atelier. Small practices that form rapidly, they gain a lot of work very quickly if they identify a particular niche for their kind of work. I think in formal terms as a practice they've only been together for 1 year. The projects you'll see tonight will be from the BMW, I think you're going to see, possibly, UN Studio, from Zaha, the funicular, and 1 or 2 other small works that we're going to see. What's particularly interesting about this practice is there are 2 architects and 1 computer scientist, and Fabian says he doesn't want to be a designer, but what I think he does is design. He says he doesn't because design is kind of loosely defined, and he only wants to deal with things that are properly defined. But what we see, I think, you will see tonight, is the gap that they occupy between the first, what in ancient days would have been called sketches and are now called kind of 3D renderings that win competitions, the world in between that and the materialized complex geometry that we see built on site, the world in between that is what Fabian is going to show us tonight.
Thank you for the introduction. Maybe I can prove that I'm not only interested in well-defined problems, but I'm going to show you a few projects that we've done over the last years, and I'm starting with a completely different thing. I'm starting with an experience I had more than a decade ago when I was allowed to visit a secret laboratory in my hometown, Munich. After I got dog-tagged with an RFID visitor pass and went through a metal detector to find hidden cameras, and actually had to pass a 1-person entry lock that weighed me and noted the mass of my body on the chip I was wearing around my neck, just in case I would grab something and try to smuggle it out afterwards. And then I was allowed to enter the halls where BMW produces prototypes of their to-be driving machines. I can't remember if I really saw or had a glimpse on one of the then confidential SUV studies that were standing around there 10 years ago. But there was one thing that impressed me incredibly, a big gray cabinet in one of the corners that was introduced to me as a stereolithography printer. Brand new, mind-bogglingly expensive. And you can see one here. I nicked the image from stereolithography.com, one of the manufacturers. And through the glass panel in the door, I could see a laser beam zigzagging through a clear fluid, and out of nothing materialized the complex, curved, streamlined form of a washer fluid tank. And I was stunned because I, of course, expected that they would use their top of the range machine to build streamlined car models of their designs. Instead, they used it to produce one-to-one prototypes of engine intestines for the reason to test or to streamline the assembly process. So they built one-to-one mock-ups of whole engine compartments to test the serviceability of the thing in very early design stages. In other words, to test if a mechanic would break his fingers when trying to repair the washer fluid tank in there. You can find it on the very left-hand side of the image here. and I would break my fingers if I tried to get this out and in again. A few years later, this manufacturing technology, not the same, but others, have become ubiquitous. You have gypsum printers in almost every architecture school in the world. They're proudly presented on the website. Students are proud of the intricately shaped models they're able to print. Some of them beautiful, some of them resemble washer fluid tanks, probably. Some of them are downright ugly. But of course, they mean something completely different. Architects have always forcefully worked on representations of their actual work, buildings, be it scale models, be it plan drawings. And usually they are very conscious about the fact that they're working on representations, and at some point the one-to-one production problems have to be solved. When I was studying, my professors were hesitant about using CAD in education because they were afraid of the scalelessness of CAD models. And when CAD systems learned to deal with the mathematics behind splines and NURBS, something that was invented in the car industry actually, I somehow thought maybe they were right a bit. When I presented my first clumsy CAD drawings to them, they were really not that good, but I could hatch square meters of plans. And now, when digital fabrication technology really becomes ubiquitous, I think this threat to scalelessness has reached the physical world a bit. And I sound a bit like my former teachers, which I don't like very much. So let me explain this on an image. One of the first projects we did when still at the ETH in Zurich was this. This is Inventioneering Architecture. It's an exhibition platform for a traveling exhibition of the 4 Swiss architecture schools, designed by Instant Architects. The client is the ETH Zurich. And when we entered this project, we were asked to think about fabrication methods for this. What we had was a CAD model and a scale model 1:50 of the platform made from, I think, styrofoam. And the question was, how could we manufacture this? How can we make a platform that is 40 meters long, 3 meters wide, 1.5 meters high, and that is a traveling exhibition, meaning it had to be assembled, disassembled, shipped, assembled again for a couple of times. And the designers thought, well, you're the computational guys, can't we use something like CNC milling? So it looks like a landscape model anyway. And to use a CNC router to do landscape models is a pretty straightforward thing. You have a 3D model of the landscape you need, you feed it into a standard CAD-CAM system, then the CAD-CAM system somehow calculates the tool paths, and then you have a rotating milling bit driving around in foam or wood and taking away the excess material until the final model is left. Very nice and very easy and very straightforward. If you have a 1:50 model of the thing, it might take, let's say, an hour of milling time. How long would it take to mill the 1:1 full-scale thing? 50 times as long? Actually, you have a thing that is 50 times wider, 50 times higher, and 50 times longer than the model. So altogether, you have 50 times 50 times 50 times the excess volume to mill away, which means the full-scale thing takes about 125,000 hours if you use the same tool, which is roughly more than 13 and a quarter years if you take the leap years into account. So definitely not working. You can, of course, change to a bigger mill. This is one I got to see in a shipyard in Norway. And when it's not used to mill the inner cladding of the Oslo Opera, it's used to mill foam cores for speedboat hulls. The working radius is roughly 10 times the size of the mill you saw in one of the first pictures. The tool is pretty much 50 times the size. And And as you can see, that comes at a certain cost, namely you reduce the resolution and the precision of the thing. But of course you can do larger models with it. But can you do it faster? The problem is you have a 50 times larger tool, but you have to drive it at 50 times the speed to get the same overall speed in the model again. Which means if you drive the tool in the first mill at 1 meter per second, you'd have to drive this at the speed of the average speed of a BMW on a German Autobahn through the material, which just doesn't work. 180 kilometers is not possible. Why am I telling you this? The problem with fabrication methods is that, good old rule, volume is proportional to scale to the power of 3. And the problem is that weight, production time, and cost of logistics is proportional to volume. So the basic message is fabrication methods are not scalable. Different ways of thinking have to be applied if you want to blow up models to real size. So what did we do? Good old engineering trick. If you have a large problem, chop it up. In this case, we chopped it up into 1,000 slices of 40 millimeters each. So this is the whole platform. And this is how it's built. It's 1,000 cross sections milled from 40 millimeter MDF, medium density fiberboard, and then put upright and placed next to each other. And the trick here is that they're interdigitating from both sides. So you have the path where people should walk along the platform, clearly marked by the closed areas. You save a third of the material, and you have the exhibition space marked by the gaps, so no one will step on it. And you don't even have to paint the path onto the thing. And as you can see, you have a vertical board supporting the whole thing. And this is actually just a small selection of the 1,000 rafters, as we call them. Of course, if you need to have 1,000 different components manufactured, you have to think about the manufacturing process a bit. So it only works if you have a little script that takes the 3D model, chops it up into 1,000 slices, nicely puts them flat on a sheet, arranges them nicely on 126 raw MDF boards, generates the G-code and sends this to the machine directly. So there is no CAD/CAM system in between. We directly generated the code that is driving this 5-axis CNC cutting machine. And then you have large heaps of components stacked on top of each other. As you can see, they're really all different. And this is what the whole thing looked in the end when it was finished. This is the opening in San Francisco. Pretty nice. Oops, that was too much. Here. So the trick is you cannot scale it. What happens? Sorry. Yeah. So what we're trying to do, and the basis our company is founded on, is actually the firm belief that architecture is made from components. There is no use in trying to make architecture from homogeneous materials and mill them from foam blocks or print them with dust printers or whatever, because the sheer size of it doesn't allow to. The building blocks you use can be either quite simple, like these bricks there, and you can put a certain effort in assembling them, or you take more complex building blocks and take a certain effort in prefabricating them and save construction time on site. Complexity in this case is not meant, or does not mean necessarily curvy forms or rocket science materials or manufacturing methods. It's a term that we take from information science, and it actually describes how much information you need to describe a system. So how much information is embedded in the system. If you have pile of bricks, there's not very much information in it. The bricks are all the same, more or less. They have the same size, the same material, and the only thing that distinguishes a certain brick is its position and orientation in space. And if you don't care about the position and orientation, because it's just a heap, there's not very much information in there. But if you take the brick and assemble it in some sort of a pattern, like a mason does, you add information, and you have to make a certain effort to do so. If you have a very simple pattern, the effort is not very high, but you can have more complex patterns, so you alter the position or the offset from one brick to the other, or you alter the orientation of every brick, a little bit like our colleagues from Zurich Grammatio Cola are doing. They'll be here, I think, in 2 weeks from now, so you see more of those pictures. I only show you one, because they are using an industrial robot to do so. And they call this informing the wall. So they add information to the system of the wall by adding information in form of the different orientation of every single brick. Another way, of course, is you don't add the information by defining different orientations, but you add the information by taking different shapes or altering the shape of the component, as we did in the Inventioneering Architecture project. And here, please note that here the heap of components already includes all the information, provided that they are nicely numbered and you can sort them, because you just have to take them and they snap into place and you don't have to think while assembling it. Why am I telling you this? The interesting thing is that the effort actually stays the same. If you have a mason, he needs a bit of training and maybe he needs a bit of thinking while he's working, especially if he has to do a complex pattern, but the rest is actually just moving material, doing things. If you have a robot, it doesn't have to think very long because that's what it's built for, or it has a computer, a controller somewhere in the background which is thinking quite quickly. It's very quickly in moving material, but it has to have a rather long training phase in the first place. So the effort to program the robot is there. The effort stays an effort. That's for one thing. The other thing is the effort shifts from handling the information to from handling the material to handling the information. And that's actually what we're trying to do, is we're trying to shift as much effort as possible from handling the material, from handling the atoms, to handling the information, to handling the bits. And that's what we call adaptive building systems. The problem with complex shapes, like here the Mercedes-Benz Museum is, that they contain a lot of information. You need a long list of data to describe these buildings. And the information doesn't go away. It even becomes more and more during the process. You can try to find rules in there. You can try to find relations between the tangency of some curves or whatever. But actually what you need to do is to have the information in some sort of a model and get it out and define, like here, the layout of the columns in the facade you see up there. And this complexity, this information doesn't go away during the process. The trick is to get it down the chain, the process chain, as smooth as possible. So if you start with a design and define some shape geometry, and you add material properties in the manufacturing method during the construction and dimensioning and detailing, so you end up with component geometries of a couple of hundred or thousand components, and then you add manufacturing process information and the tooling during defining the manufacturing information. You end up with something like a process geometry, what we call it. And then you add maybe a few machine-specific information bits and generate the machine data, and then you go into production. So the trick and what we're trying to do is making this as frictionless as possible to get the complex information down the chain without any losses and without any loops, if possible. Let me try to explain this on another example. This is what Mike already mentioned, the Hungerburg barn in Innsbruck. It's been there for about 100 years, but it has it was completely rebuilt. The 4 stations are designed by Zaha Hadid, and they all have a concrete platform where people are standing on and a sort of a free-form blobby roof sheltering the whole thing. The platform is not the problem. The problem is the roof, and especially the cladding of the roof. But this was solved by Bolling and Grohmann, the engineers, and Pargitz, the steel contractor, by finding someone in China who was able to bend glass panels into doubly curved shapes. This is actually a rather distorted picture from the production. They built steel tube tables where they then form the glass panels by heating them up and sinking them on the steel tubes, and then they use the first glass panel as a mold for the second final glass panel. So it's quite an intensive thing, but it worked in the end. The steel under construction of the stations was pretty straightforward too. That's cross sections cut from steel plates, and the last problem to solve was the connection between the steel and the glass. A few alternative solutions were developed, because of course the glass is meeting the steel under construction at various angles. The angle changes every meter on the thing. And there's basically 2 possible solutions. Either you have a movable joint, so you can have a universal joint that you mass produce by sand casting or whatever, and then you have to adjust the movable joint before assembly on site, which results in a rather tricky measuring and adjusting task on site. And that was the final solution. You have mass customized joints there, and this is the final thing. It's a rather simple profile made of polyethylene plastic, to say 60 millimeters wide, and it sits on the steel plate and changes its angle of bank on the outside, exactly like the inventioneering architecture rafters did. And then there are small metal strips glued to the glass panels, and those are then screwed down to the plastic profiles. On a test run, it looked like this. So you see the vertical steel plates in the cross sections of the station. You see the black profiles running around those cross sections, and you see the twisted and bent glass panels that are screwed down to that. Actually a very nice thing, because the material is rather cheap. The problem is, of course, you end up with 2.5 kilometers of custom cut profiles that you have to manufacture somehow, somewhere. But since we knew how to deal with the inventioneering architecture project, this was really just a follow-up project, more or less. We received the geometric data in form of spline curves from the engineers, defining the 2 outside curves of every profile and the inside curve where the steel panel was sitting, and normal to the face, so we could decide whether it was okay or not. We had to segment the whole thing so it would fit on the raw boards of the material, and define where to drill holes to fix it down to the steel plates. This information was then going back to the engineers, who gave it to the steel contractor, because they had to take care that the holes in the steel would be on the right positions. Then again, you have to lay out the whole thing flat, nest it nicely on boards, generate the tool paths for a 5-axis cutting machine, generate lots and lots and lots of lines of G-code that are really just mostly X, Y, Z, and a few AB coordinates. But then the trick comes, how do you integrate the whole thing into the assembly process? So this is the assembly, the manufacturing documentation for the guys at the milling machine. Every single board that was cut had such a layout sheet so they could identify the pieces. Every single piece had a little sticker with an image on it so that you could identify the pieces on site, and to reduce any error possibilities. And then the whole thing goes into production. You see here a raw board. First the the holes get drilled, and they screw it down to fix it in the machine. Then you have 2 goes with the cutting tool, and in the end, the whole thing looks like this. So that's about 20 profiles out of 2,500 on one board. Nicely numbered, so that you can find it on the construction site and find the right spot for it, and then stacked and delivered. And this is what we actually try most of the time, to have a system of, or a custom system of building components that are propagated over a structure, that are as simple as possible to define and to manufacture, but actually define the whole geometry that is needed around it. So in this case, the angle where the glass meets the steel in the component. So there's no adjustment on site anymore. You just take the piece, put it in the right place, screw down 2 bolts, and that's about it. And this is what you see on the construction site where the thing has been assembled. And this is with the glass panels on. So the idea here is to move the complexity from the material world into the informational world as far as possible, and don't have to deal with measuring and adjusting on site, but prefabricating the thing and then really just putting together the pieces in the end. This is what we're trying to do, having this straight process chain from the architect who's defining the shape geometry to the engineer who is doing the construction work over our company, where we then segment the whole things, develop a parametric model, develop the fabrication code, and hand it over to the manufacturer. This is, of course, a rather academic view of the process. In the real world, it looks more like this. You have a shape geometry going to the engineer, which defines a construction geometry, which we take, chop up, and give back a part geometry to the engineer, who passes it on to the subcontractor to drill the holes in the steel, while we give the CNC code to the manufacturer that does the manufacturing and delivers the parts to the subcontractor onto the site. And if you look at the contractual situation behind that, it becomes even more difficult. Because, funny enough, I didn't have a contract with the manufacturer. Our company had a contract with the engineer, who had a contract with the subcontractor, who had a contract with the manufacturer. But I was more or less only talking to the manufacturer. So don't ask me about liability problems in here. But in between the 5-axis cutting machine and us, there were at least 2 lawyers in case something went wrong, which didn't, fortunately. So the actual task is about 50% of the work goes into optimizing this process and this seamless integration into the building process of the whole thing, and only the rest goes into developing parametric models and then delivering data to whomever is using it. One point that we're trying to do is learning from mass customization. Coming back to the automotive industry, they still take most of their efficiency from the vast numbers of cars they produce. But since the times of Henry Ford, the things have changed quite a bit. You cannot only order cars in other colors than black, you even get them in other colors than black. The new Fiat Cinquecento comes in theoretically more than 500,000 different configurations. You just have to choose. So from mass production, it's really going into the direction of mass customization. The customer is deciding what he wants to have. The problem is, if he wants to have something completely different from the predefined options that are in the catalog, it becomes really expensive. Unfortunately, architects and their clients usually want something completely different. So mass customization doesn't really work. Fortunately, they work on a completely different scale, and that's what we're trying to exploit. And I'll show you a last project. The EPFL Learning Centre by SANAA in Lausanne library and lecture halls for the EPFL. The main design feature is a nice hilly landscape that is formed by this one-story building. It's actually a steel construction standing on a 20,000 square meter slab of concrete that is nicely undulating up and down over 5.5 meters. You can cast reinforced concrete in almost any shape. The problem is, how do you build a formwork where you can cast it into? The problem is standard formwork systems don't deal very good with doubly curved surfaces. They're very good at orthogonal things and straight walls, but not at this stuff. The idea of the general contractor who is building this is to subdivide the doubly curved part of this slab, 7,500 square meters, into nice little squares of 2.5 by 2.5 meters, and use a mixture between a standard formwork system and custom built formwork. By building scaffolding just under the desired surface of the concrete and filling the gap with a box or a table, as they call it, made from 7 vertical cleats cut from plywood and then covered with another plywood sheet on top. Pretty straightforward. So you have 7 cleats, you have 6 braces to stiffen the whole thing, you have 2 standard beams underneath, you can see them here, and you have a few steel bits pushing the whole thing up a few meters into the air. So now you only have to multiply this by 1458. So this is what we actually did in the end. This is what the whole thing looks like. This, just to give you a few figures and to impress you, the scale factors. So the total slab area is 20,000 square meters. The doubly curved portion of it is 7,500 square meters. The number of tables that were built is 1,458. The number of cleats in those tables is 9,744. The total cleat area is just a bit over 10,000 square meters. And if you add the covering sheets and the braces, you end up more or less exactly at the same figure that is the first one in this table. 20,000 square meters of plywood were used in this formwork project. For every of those 1,458 tables, there's a plan drawing like this, which is a nice phone book in the end. So you have all the cleats of every table there, nicely dimensioned. You have a few additional informations. Of course, there's lots of tables with information. There is, for every single of those almost 10,000 cleats, a production file with the G code, or in this case, the MPR code that is driving the 4-axis mill they're built on. The manufacturer then nests the cleats nicely onto roll boards. This is where they are cut. And then they are being transported from the eastern part of Bavaria halfway to Lausanne to the builder of the formwork in nice little stacks, and they put them together and build those tables. Of course, they're nicely numbered again, so they can find them on the construction site, and then they stack them and wait until the next truck comes, 1 out of 150 that takes them the last 100 kilometers from Bern to Lausanne. There was a test run just 2 weeks ago where they took 6 of those tables. You can't see them very well in here, but that's what the formwork looks like then in the end. And this is what the outcome looks like. And this is a combination of the cleats and the braces and the final tables. And this is what it should look like in about 3 months from now, before they pour the concrete into. So the thing is, it's working really based on the numbers. If you start thinking in seconds, you can just do a quick calculation and see that if you have 10,000 pieces, if you save 1 minute in the planning and production per piece, this saves about 1 man-month of work in the whole process. And if you take that into account, and you have an effective planning time that boils down to 25 seconds per component in the end, you can try to sit down and draw every single cleat and cut it with a, I don't know, handsaw or whatever. And you see that there is quite a bit of money and effort to be saved in this if you try to optimize this process. And not only optimize the production process, but also optimize the logistics behind it. And that is basically what we're doing. So to put all together, fabrication methods do not scale. I think, and I'm pretty convinced, that printing or milling real-size architecture from homogeneous materials just doesn't work. I'm happy to see anyone proving me a different thing, but I don't believe in that. Architecture is made from components, and for budget reasons, standard materials have to be used, usually. So there's not very much rocket science materials out there in building because it's simply too expensive. Most of the materials used in building are either one-dimensional, straight beams, or two-dimensional, flat sheets. And then they have to be bent or cut or whatever into the appropriate form. And it is expensive and is difficult. And the biggest problem with the Hungerburg funicular was to have to meet the tolerances in the glass panels. They were bent in a rather manual process, but then they were laser scanned afterwards and compared with the CAD data they had to find out if they meet the tolerances, and if not, they were shredded and done again. And I think they shredded quite a bit. And even the formless material concrete needs a formwork. In our case, 20,000 square meters of plywood chopped up into nice pieces and built on tailors again. Complex shape is a lot of information, and the handling of information consumes energy. So there is no way around it. If you have a complex shape and you need half an hour to describe the shape to someone, it needs quite a bit more time to define a couple of thousand pieces that are forming the shape afterwards. So the idea is start with a well-defined complex shape in the first place. Usually we have to deal with models that are not very well-defined, but they result from someone tweaking NURBS and splines for a couple of days and weeks, and then you actually can throw them away and start again because they're completely unusable for production quality. And the trick is to reduce friction through parametric models and seamless digital production chains. So if you have the information in the first place, try to get it down to the manufacturer as smooth as possible without any loss and without any loops, because that is what's actually bringing in the effort in the whole production. And parametrics don't come for free. So you can have a robot, you can have a machine, but to train the robot to program all the scripts doing it comes at a certain cost. But the trick is that the sheer scale of building projects redeems the effort. So if you have 10,000 cleats or even less, so it starts at maybe 500 different components, that it pays off to sit down, think a bit, do a parametric model, and build up one of those production chains. In the end, size matters. So it's not a naive way of scaling up the complex model and scaling up the manufacturing method. It's the sheer size of architecture that allows mass customization on a different level. Not on a level where you have to find 10,000 different customers to buy your car before the effort to plan and develop it pays off. But it's working within one single project because of the sheer size of the project and the sheer number of components you have in there. So what we're doing is actually really developing project-specific mass customization chains and try to save money with that. And that brings me back to the last slide and back to the BMW story from the beginning. Size matters. This is a 50-year-old car and probably the smallest one that was ever built in Munich. Thank you. And I expect as much questions as possible.
Okay, thank you, Fabian. I think we'd like to open the floor to questions. Fabian is willing to answer anything, I think. Any questions, please?
Thank you, Jalal.
All right. Is this working? Yeah. Just going back to that diagram about the academic way of from design to production.
You want to see it again?
Well, I know it. Can show it to people.
Okay.
What my comment is, there was, I mean, the loop. It seems your loop is always between engineer, fabricator, contractor, and yourself or the facilitator. Have you ever tried to go back to the design board, to the architect? I mean,
it depends. So we have actually two offices. One is in Zurich, where I'm based, and one is in Stuttgart, where Arnold Walzer, our partner, is based, and he's working much closer with the architect. So he was the guy doing the master model for the Mercedes-Benz Museum. He's working with Renzo Piano, or has been working with Renzo Piano on the thing in Cologne, this whale thing. He's on the front side of the production chain, more or less, whereas we in Zurich are more dealing with the manufacturing and the engineering side in the end. Actually, we would like to work more on the architecture side. It proves to be difficult. Mainly because it's difficult to get the information from the manufacturing end up, in this case, to the design side. In the building process, usually the guys doing the dirty work in the end are the last ones that get contracted. And as long as they don't have a contract, they keep the information they have and don't give it out that easily. We're trying to bridge this a little bit, just with the experience we now gain with different projects and different manufacturers, different manufacturing methods. So to gather the information from the manufacturing side and be something like a relay station that maybe can handle up or hand up the information to the design side. But it is difficult, and we would like to see more architects coming to us and talking to us about fabrication and digital fabrication chains that we have up to now.
I have one, because you about the digital model. You don't like splines.
I'm working with them all the time. I like splines, no problem. Was that the question?
Do you find that most of your architectural clients work with them and that you rebuild the model? Story we hear from engineers all the time. And they build a different model. The architects have a digital model. The engineers have a model.
Yeah.
The contractors have a model. And you guys are also making a different model.
Unfortunately, most often it is exactly like this. Yeah. And I think it might be an unsolvable problem, because the needs of architects in a design phase and the needs of engineers and the needs of manufacturers are different. A good-looking NURBS model is nice to do renderings and win a contract. But if you have whatever sort of roof or concrete slab going along a long spline, and you want to look along this edge and you don't want to see any kinks and stuff in there, you need to have a well-defined spline on NURBS surface. That is not what architects in the design phase are caring about, and I can completely understand that. But it means that you either have to remodel the whole thing from scratch, or you have an architect that is able to tell you, with this spline I was intending to do this and that. So these are the 7, 8, 9, whatever, how many points that are defined very exactly, and the rest is just a smooth curve through there, and that would be the perfect thing. So as if in some cases we managed to come across architects or across someone who was doing the model, who was telling us, okay, I don't care where the surface is going in between those points, but they have to meet those 2 points. And that's the thing you need. What you don't need is a NURB surface that has 2 points where it should be, and then about 2,000 points in between that just came there by accident while tweaking and twitching the NURBS model.
Fabian, I would have a question. I think you make a really stunning and convincing argument about the relationship between design and feasibility with regards to materializing a design. But coming back to the question that Jalal asked earlier on, would you not somehow agree that questions of materiality and manufacturing, if they would appear much earlier in the design process? You had one diagram with gray arrows pointing upwards, where materiality and manufacturing came way past the design phase. Would it not also allow to address questions of sustainability? And I'm not saying that merely because that's a topic that's flying around now everywhere, but it seems to me that a lot of the architectural projects that are designed today, iconic projects, really fly into the face of anything that could be called sustainable. And so, wouldn't your engagement much earlier in the process help with that as well?
It could be healthy, let's put it like this. We can have a long argument if it is in any way sustainable to have 20,000 square meters of plywood chopped up to have a formwork for this, or if there's any other way to do that. I don't know of any other way to do that right now. Probably someone has a bright idea and comes to me afterwards, but I'm afraid construction just started this week, so we're a bit late. But of course you're right. Lots of those projects are because I can projects. And I have no answer to this question. I know that if you start early enough to think about production and all the things that come with it, usually the things get better in the end. So the old Oscar Wilde thing, the most beautiful things come from people who want to do something useful, and the most disgusting things come from people who want to do something beautiful. Yeah, but I don't want to argue too much from the engineer side here, so being confronted with too many architects and designers.
One in the front and then one behind.
Fabian, I wanted to know, how do you deal with these extra information exchange between the designer and the subcontractor, contractor? The softwares, for example, one designer works with Maya or with NURBS or with Mesh, who works with other things. How do you do that? And the second thing is, for your construction thing, does your drawings are parametric also? I mean, do you lay out every single piece by is it automatic, or how?
Yeah. So the integration from the CAD system side is a thing that is different in every project. Right now, funnily enough, most of the clients we're working with use Rhino to define complex shapes. So we use Rhino too. I'm pretty happy with that. It's got a perfect programming API. You can script it. You can go in there with VB or C#, no problem at all. Arnold in Stuttgart has worked with Autodesk for a long time, programming lots and lots of opening and closing brackets in Autolisp. So what we're trying to do is actually take what's there already and avoid to have another interface in the project where data is getting lost. So if there's one CAD system in the project already, or is the main software that is used in the project, we're trying to use this software to get back and forth. On the other hand, what we're trying, for example, with some manufacturers, is to program our own interfaces between specialized CAD-CAM systems, for example. So there is a project we're doing right now. It's the Centre Pompidou in Metz by Shigeru Ban, where a special CAD-CAM software from timber engineering is used, and we're trying to implement a special interface to go back and forth between there. So even the timber guys, the manufacturing guys, are using Rhino to define the geometry, but then have to go into their CAD-CAM software to drive the 5-axis machine with that. I don't know if this answers your first question, but the answer is we take whatever we can get and whatever is useful on the project. The second question, the answer is clearly yes. I don't want to lay out 10,000 different fleets. I write a little script that does that for me. And then the question is always, how do you integrate this into the process? So in the case of the Hungerburg barn, we did the nesting, for example, of all the pieces. In case of the EPFL thing, the 10,000 cleats were nested by the manufacturer in the end because he had the software. So it really depends on where do you put the data into the process again, and then it starts from there. But usually I have studied computer sciences to not click the same button 10,000 times in a row, but write a little program that does it for me. Barely. So the question actually is, what is driving the design? Is it a top-down thing where you first define the shape and then find an appropriate component system for the thing, or do you have a system first and then do a design with it? I don't want to be too much going towards one or the other side. I think that having a system and then making a design after the system is probably not the best way. I like it more to have a design and then think of a usable system. But that might be just my approach to do that. On the other hand, it is, of course, interesting to have some idea about the system and then try to find out what you can design with it, and maybe have a few loops and alter the component or the system to match your design ideas in the end. So I think it's a process that comes from both sides. I don't think that we should go into the direction of Konrad Wachsmann et al. And define systems and then try to put things together with them. At least you wouldn't end up with the architecture, with this iconic architecture that is obviously a need right now, I think. I think the invention of computer-aided design and on parametric design and computer-aided manufacturing actually enables us to define systems after we have an idea of the design. So we find the system for the design and not the design for the system. But that's only my opinion.
Other questions, anyone? Can you share? Give us the New York version.
Apart from trying to move towards a more streamlined flow of information, where do you see this kind of approach going in the future, maybe in the next decade, as far as the techniques you use, the technology that you're trying to
Difficult to tell. That would reveal my business plan for the next 10 years. No, actually, I don't know. I think that
Some business.
I think that the development will keep on. There is tools like generative components or whatever you call it in Rhino. It's coming up now.
Explicit history.
Explicit history. Thank you. Coming up where you have some sort of tools that allow you to build those systems like we do now. We're doing it actually the hard way, programming the whole stuff, because we don't have really usable systems at our hands that we can use to go all the way down to the fabrication data. But they will come, of course. It will only take a few months or a few years. I think probably more to the few months side. And the thing is, I don't expect everyone working in this way, or we're doing, because as Mike said, I don't regard myself a designer in that case. I regard myself as someone who is looking for abstract systems or patterns in design, and then define a system and try to break it down into components and do parametric modeling. This is an approach that is somehow got implanted into me when I was studying computer sciences, probably, or even before. And I know that there is people out there who think completely different. And I absolutely like that, because they can take care of the other stuff and I take care of the systematization and abstract thinking, and that's fine. The problem is more to find a common language in between those two. And I hope and I look forward to see more architects and designers being able of expressing their needs or designs in probably more abstract terms, so that you can really formulate a parametric model on top of that. You don't have to do it on your own, but you have to talk to someone like me so that I understand you, and then we can go on from there. So that's what I hope will emerge from all this parametric stuff.
Other questions, anyone? Okay, I think we're going to have a beer upstairs. So